let's discuss the current quantum mechanical model of the atom. In the quantum mechanical model, Bohr's energy levels are now called principal energy levels. They are definitely not paths for the electrons to travel. Principal energy levels are divided up into sublevels, labeled as S, P, D, and F. The number of sublevels present in any given energy level is equal to the energy level number. For example, energy level 2 has 2 sublevels. That would be S and P. Energy level 3 would have 3 sublevels, S, P, and D. Sublevels are further divided up into individual orbitals. The S sublevel has only 1 orbital. The P sublevel is 3 orbitals. We saw those earlier. Remember, they differ only in their 3D orientation. The D sublevel has 5 orbitals, and the F sublevel has 7. Knowing this structure for atoms, we can write what is called an electron configuration for a given atom. This tells the location of every electron in the atom. The notation that we use is a repeating pattern of the principal energy level number, the letter of the sublevel, and an exponent representing the number of electrons in the sublevel. There are several rules governing the location of electrons in an atom. Here are 2 that we need to know now. First, only 2 electrons can exist in a single orbital. Second, electrons always exist in the lowest energy orbitals possible. This means we need to know the order of orbitals in terms of their energy. There are 2 ways to know the order of orbital filling. You can draw and use a diagonal diagram, or you can use the periodic table. To draw a diagonal diagram, start at the bottom with 1s and write the sublevels in columns and the principal energy levels in rows. Then draw diagonal arrows from bottom right to top left. Now you read 1 arrow at a time to know the orbital order. The first arrow at the bottom shows 1s. The next arrow shows 2s. The next arrow shows 2p, followed by 3s, and so on. This method is functional, but a little cumbersome to use. What's faster is using the periodic table to tell you the order of the orbitals. The periodic table is broken into blocks associated with the sublevels of the outermost electrons of those atoms. For example, any element in the first 2 columns has their outermost electrons in an S sublevel. These 2 columns are called the S block of the periodic table. Every element in column 1 of the periodic table has 1 electron in an S sublevel. For all these elements, their electron configurations end with the highest principal energy level number followed by S1 every time. For column 2, their electron configurations end with some number followed by S2. Notice that helium is not drawn in this block of the periodic table, but it is still considered an S block element. The first principal energy level is so small that it can only hold 2 electrons. Helium, with 2 electrons, has that level filled, which is why it definitely belongs in the last column with the noble gases and their full outer shells. Helium is an S block element because its last electron is in the 1s sublevel. The 6 columns on the right-hand side of the periodic table constitute the P block of the periodic table. All these elements have their last electrons in a P sublevel. Likewise, the middle transition metal section is the D block, and the inner transition metals are called the F block. The principal energy level for any set of orbitals is related to the row number. For S and P block orbitals, the principal energy level is the row number. For D block orbitals, the principal energy level is one less than the row number. And for F block orbitals, the principal energy level is 2 less than the row number. Let's look at a few examples. Write the electron configuration for the element sulfur. Let's do this off the periodic table. Start at the top left of the periodic table, go left to right, top to bottom, and write each level and number of electrons until you get to the element sulfur. This means going through 1s2, 2s2, 2p6, and 3s2. How far into the next level do we go to reach sulfur? We go 1, 2, 3, 4 squares in. So the electron configuration ends with 3p4. That gives us 1s2, 2s2, 2p6, 3s2, 3p4. Let's try bromine. Starting at the top, we again go all the way through 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. We then reach the D block. Remember that the principal energy level of these electrons is 1 less than the row number, so we'll write 3d10. Then we have to go 5 squares into the 4p section to get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. You probably recall from your Chem 1 class that there's a shortcut we can use here. We can actually start at the noble gas that precedes bromine on the periodic table, in this case argon. Noble gases have a full outermost energy level. This means their arrangement of electrons is very stable. Noble gases never spontaneously chemically react. So instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, we can write AR in brackets. We then write the rest of the electron configuration in the same way. Take a look at the element yttrium. Starting at the previous noble gas, we would then go through 5s2 and 1 block into the 4d section, giving us Kr in brackets, 5s2, 4d1. We're going to do one more example, the element platinum in row 6. There's something you need to remember about rows 6 and 7. Notice here that the atomic numbers jump up. This is where the inner transition metals fit into the main body of the periodic table. The inner transition metals actually fit into the periodic table after the elements lanthanum in row 6 and actinium in row 7. Lanthanum is filled at 6s2, 5d1. Likewise, actinium ends with 7s2, 6d1. Electron configurations of the inner transition metals vary greatly. They're not predictable in this method that we're using for the rest of the elements. So you won't be asked to write their electron configurations this way. When you look at elements beyond the inner transition metals, what the periodic table actually shows is one electron going into the D sublevel, then the F sublevel filling completely, then further electrons being added to the D sublevel. we're going to simplify this just a little bit. When you're asked about elements beyond the inner transition metals, you know that the F sublevel is completely filled. So after the S sublevel, 6S or 7S, write the full F sublevel. Then start on the D sublevel after that. So for the element platinum, I would start at xenon, then write 6s2. Then I would include the full F sublevel. Remember that for the F block, the principal energy level is the row number -2. The top row of the intertransition metals is from row 6 of the main table, so we'll write 4F14. Then we go back and start at lanthanum in the D block. That would give us 5D8. The electron configuration then is xenon, 6s2, 4f14, 5d8. Closely connected to electron configurations is the process of drawing orbital diagrams. Electron configurations tell you how many electrons are in an entire sublevel. Orbital diagrams break it down a step further to show you the location of the electrons in each individual orbital. In an orbital diagram, you draw a box or a line to represent each individual orbital. You draw up and down half arrows to represent the electrons. We talked about a few rules for writing electron configurations. Here we need a few more rules that apply to orbital diagrams. First, electrons enter degenerate orbitals singly before pairing. The word degenerate here means of equal energy. All the p orbitals in the 2p sublevel are degenerate, for example. They are equal energetically. The only difference between them is their orientation in 3D space. What this rule means in simpler terms is that electrons won't pair up in an orbital until they have to. Additionally, when they do pair up, electrons in the same orbital must have opposite spins. We use up and down half arrows to represent spins. Draw an orbital diagram for the highest occupied sublevel of nickel. First, what is the highest occupied sublevel? In other words, what is the last thing you would write in its electron configuration? That would be 4d8. How many orbitals are in this sublevel? Because it's a d sublevel, there are 5 orbitals. The number of orbitals has nothing to do with the principal energy level. The number of orbitals is determined by the type of sublevel. S-type sublevel, 1 orbital. P-type sublevel, 3 orbitals. D-type, 5. F-type, 7. How do electrons fill these orbitals? Hund's rule says that electrons won't pair until they have to. Even more specifically, Hund's rule says that for degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin is maximized. Putting all that together means put electrons into separate orbitals drawn with the same spin for as long as possible. When each orbital has 1 electron in it, then you have to show electrons paired. Remember that the previous slide said that electrons in the same orbital must have opposite spins. The second electron in each box must be drawn oppositely. What if I started pairing electrons from the right-hand side? Is that a problem? No, because all these orbitals are degenerate. They are equivalent. I could choose any 3 boxes to pair the electrons in. What if I'd use down arrows first? Is that okay? Yeah, that's okay too. You just have to write the opposite arrow when you pair them in an orbital. Draw an orbital diagram for the highest sublevel of the element tin. The highest sublevel reached is 5p with 2 electrons in the sublevel. How many boxes do you draw, and why? You should draw 3 boxes because it is a p-type sublevel. You have 2 electrons to put in the boxes. They will go in singly. A common question that relates to orbital diagrams is how many unpaired electrons in an atom of blank. Your answer is based off of the orbital diagram for the highest occupied sublevel in that atom. How many unpaired electrons do you see in that orbital diagram for nickel? You see 2 in those last 2 boxes. Here you have electrons in a box without a partner. That's an unpaired electron. How many unpaired electrons in an atom of tin? The answer is 2 again. What is this third empty box? It is an orbital that is currently unused. There are no electrons in that orbital. To finish, there are 3 rules that we've seen regarding the placement of electrons in atoms. First is called the off-ball principle. This is the rule that tells us electrons fill lowest energy orbitals first. Please, note that off-ball is not the name of a dead scientist. It's a German word that means to build up, to construct. Hund's rule is named for a dead scientist. It tells us that electrons won't pair up until they must. And the Pauli exclusion principle says that electrons in the same orbital must have opposite spins.